So what we have seen up to now in our proof is that each representation decomposes into a direct sum on those smaller spaces. So let me write this down where we are. So from the arguments up to now, we have seen that each representation of the Weyl relations is actually equivalent or decomposes to a direct sum of representations which are then presumably irreducible, or which are irreducible on those spaces Hn, and this Hn was the span of vectors of the form where I'm applying my Weyl operators to this omega n. And I'm also taking the closure of this. So I have here Hn. This is the space which is generated by omega n and everything which I get from there by applying my Weyl operators. And so what I still have to see is that actually each of those guys here, the restriction of the representation to such an Hn, is actually the Schrödinger representation. And for this, of course, we are using the idea that if I have this description of the representation, then everything is determined uniquely. So the idea is that this omega n is a vacuum. Of course, now we are not seeing that this vacuum is annihilated by anything, but we know that it is in the range of this projection operator. And so the idea was that everything is generated from this vacuum, which is more or less what we are doing here. So we are taking here everything which we can get from this vacuum, but then the representation should now be determined just again by algebraic relations of the Weyl relations. So what we have to see is that the effect of our Weyl relations here is determined, and also the inner products in this space are determined. And then, of course, it has to be the Schrödinger representation. If it is determined, it's unique, so it must be the same as it is in the Schrödinger representation. So we have to see this. So let us now fix an n. So we have to show this for any n. So let us just take one of them. So we fix this. So fix n. And of course, instead of omega n, I'm now just writing omega. And put omega equal to omega n. And then maybe we have to see that everything is determined on this space, and of course this space is now a Hilbert space which is generated by vectors of this form. So maybe let me give a name to those vectors. So for real S and T, I'm denoting this by f s comma t. So this is just omega st applied to omega n. So those are just vectors in my Hilbert space, which I'm getting in this form. And of course, they are not orthogonal to each other, but at least they generate the whole Hilbert space. If I'm taking linear combinations of them and also going to the closure, then I get the whole Hilbert space. So if I see that from the data which I have, I can recover the inner product between those vectors, and I can also recover the effect of my Weyl operators on those vectors, then I see that everything is determined. And that's what we have to see. So first of all, the action of the Weyl relations on such a vector is of course clear. It's trivial because we know what happens if I'm multiplying two of the omegas. So then we have, so if I'm now acting with a w xy on such a vector fst, then of course this is nothing else than w xy, and the fst is w st acting on omega. But we know if I'm multiplying two of the w's, I'm just getting another w with some factor. And the factor, maybe let me write it explicitly. So it's 1/2 I times xt minus ys. And what do I get here? I get a w, and I have to add the argument. So it's x plus s comma y plus t. And so you see, I just have the application of some other w on omega, which is just one of the other f vectors multiplied with such a phase. So what I have here is e to the 1/2 I, so this phase factor xt minus ys, and here I have f x plus s comma y plus t. Okay, so the effect of my operators on those vectors is determined by the Weyl relations. I mean, of course, this here is just Weyl relations in disguise. It's the same information as the Weyl relation. Good. So the action of the operators is determined, and now what we should also see that it's determined is the inner product of those vectors. So it's really the Hilbert space structure is determined. So if I'm able to calculate the inner product between two such vectors just out of the algebraic relations which I have, then everything is determined. So let us check that we can do this. So again, what we need is to understand what is the inner product between two such vectors. So let us take fxy and fst. And I want to calculate the inner product between those. Yeah. So by definition, this is w xy acting on omega, inner product with w st acting on omega. Yeah, and so again, similar as we did somehow before, I mean, I bring this on the other side, and then, yeah, again, it's good that we can put the p there. Okay, so let me do it. So what I have here is omega, comma, and I have here w. If I bring it on the other side, the adjoint is w of minus x minus y multiplied with w st. And here I have omega. Yeah, and of course, first of all, this again, the product of two w's is just another w with some phase factor. And maybe I write it explicitly, so that we just see that we know everything. So this is I times, so it's minus x times t, minus, so it's plus y times t. And then I have a w of s minus x, comma, t minus y. Yeah, okay. And could we use something from before? Maybe not so clear, but what we can do is, again, I have here w, and I know I'm just looking on inner product with omega, and omega is the same as p omega. So I can, again, put a p here, because p omega is equal to omega, and then I can bring the p on the other side, and then again I have just algebraic product where I have a w between two p's, and algebraically I know this is just a multiple of a p. And then I'm really at a point where I can calculate it. So let me bring this p on the other side. And then you see what I have here now. So let's see, I mean, up to here. So it's this e factor here, e to the 1/2 I, and I have minus xt plus xt, here it should be a ys, plus ys. Okay, and then I have the w, this guy, which I have sandwiched between two p's, and there we know that I get also an e factor, namely I get e to the minus 1/4, and I get the sum of the squares of the argument. So I have here s minus x squared plus t minus y squared, and just the p. So the w's disappear, it's just a multiple of the p, and now you see I have here a factor which I can take out of the inner product, and in the inner product I have just left the p, but the action of p on omega I know exactly because this is just omega. So this is now all together. So this is now really the inner product between fxy and fst. So this is e to the 1/2 I, and I have minus x. Okay, let's see, I have it here the other way around, maybe. xt this is this. Okay, so I think this is okay as we have it here. I'm multiplying this with this and this with this. Okay, so it's minus xt plus ys. Oh, this is this factor. Then I have e to the minus 1 over 4 s minus x squared plus t minus y squared. Oh, so these are just these exponential factors which I'm taking out of the inner product. And then in the inner product I still have here this omega. And on this side only the p is left. So I have on the other side p omega. Yeah, but p omega, of course, is omega. And I have the inner product between omega and itself. And omega was a unit vector. Huh? So this is just 1. Okay, and so you see just by the algebraic Weyl relations, we have calculated the inner product between those two vectors. Huh? I mean, it doesn't really matter what the final result is. It's just important that we are able to do this just by the Weyl relations. Yeah, okay, but this means now everything is determined in my representation. If I have a vacuum, I mean, I define those guys, this FST, and then in terms of the FST, both the action of my Weyl operators as well as the inner product between those vectors is determined. And this means if I have two such representations, which are given by an omega and yeah, those guys here, then I can map those vectors FST to the corresponding guys in the other one. And this gives me a unitary mapping between the two Hilbert spaces. So this means whenever I find two such situations, they have to be unitarily equivalent. So maybe I'm writing it down. So thus all inner products and the actions of the W, X, Y are uniquely determined and so in particular this means if I have two such representations, two such representations. So for example, I mean the representation on Hn and the representation on Hm in my decomposition from which I had here, then actually I mean I can map one onto the other. So namely, let's say I have an omega where the WST act, and let's say this is in the Hilbert space H, and I have the same where I have this vacuum omega prime, and I have my operators WST prime acting on a Hilbert space H prime. For example, I mean this here is the Hn, and this here is the Hm. Then I can map one onto the other, and the action of the Weyl relations is intertwined by this, which means that the representations are unitarily equivalent. Yeah, so maybe I continue over there just to finish this. So if I have two such representations, for example those here, then I can map one onto the other. So then the mapping which maps the vector FST in one representation, and this vector was WST on omega, this maps this to the corresponding the same vector in the other representation, namely FST, let's say prime, which is WST prime acting on omega prime, then this gives me a unitary map. It's unitary because all inner products on this side are the same as the inner products on this side, because they are just determined by the relations, by the Weyl relations. So this mapping extends to a unitary map, and of course this also intertwines the action of the Weyl relations here with the action of the Weyl relations here, because the action of the Weyl relations is also determined in a unique way. Because we know this acting on this just gives me another f with a precise factor, and here it's the same. So this mapping here really is a unitary map which intertwines the action of the Weyl relations, which we have here, with the action of the Weyl relations, which we have here. Of this, the action of this, and of W prime S of t. Good, okay, but so this means in particular that all the representations which I get here in this direct sum, they are unitarily equivalent. Okay, and so in particular I mean all irreducible representations of the Weyl relations are unitarily equivalent. And since we already know one irreducible representation of the Weyl relations, it must be that they are all equivalent to this one, so namely to the Schrödinger representation. So this means the only irreducible representation of the Weyl relations is the Schrödinger representations. So thus all irreducible representations are equivalent to each other, and thus in particular equivalent to the Schrödinger representation, are equivalent to each other, first of all, and thus to the Schrödinger representation. Yeah, okay, and this then is the end of the proof. So we have seen every representation decomposes into a direct sum of those components here, and those components here, they are irreducible and they are all equivalent to each other, and in particular then also to the Schrödinger representation. So there's only one irreducible representation of the Weyl relations.